All right, let's dive into a question that sounds simple on the surface, but has actually been a real puzzle for biomechanics for decades. We're talking about a paradox at the very heart of how we move, and a new theory that might just flip everything we thought we knew about the human body on its head.
So first up, let's get right into this central mystery, the pushing-pull paradox. And trust me, it's a genuine head-scratcher once you really start to think about the mechanics of our own bodies.
Okay, think about your hamstring for a second. Its main job is to pull your heel up towards your butt, right? It's a flexor. It closes the knee joint. So, how on earth, when you're jumping or doing a deep squat, does this pulling muscle suddenly become a key player in the pushing force that drives you off the ground? The traditional models just don't have a good answer.
And see, that's the problem. The old way of looking at things, what scientists call muscle centrism, sees muscles as basically simple engines that just pull on bones. And that view can't solve this paradox. But a new theory suggests a huge shift in thinking. What if we see our muscles as hydraulic pressure systems? This new paradigm is being called structure-pressure centrism.
This entire idea comes from a series of papers by an independent researcher named Seiji Sato. He basically argues that if we look at the body through the lens of pure physics, geometry, and fluid dynamics, a lot of the old, fuzzy theories get replaced by what he calls the inevitability of hardware.
So, how do we start to unravel this thing? Well, the first major clue comes from Sato's work on what he calls bio-inspired actuators, where he built a mathematical model of our muscle and all the tissue around it.
And what his model shows is, well, it's pretty amazing. The spiral, layered structure of our muscle and the fascia wrapping it isn't just a simple bag holding everything in. No, it's a machine. A machine that's incredibly good at one thing, turning a simple pull, axial tension, into massive, massive internal pressure.
And the mechanism itself is just beautifully simple. When tension is applied along the length of the muscle, those spiral fibers that wrap around it are forced to tighten up. This makes the muscle's radius shrink, which in turn squeezes all the incompressible fluid inside. It's exactly like wringing out a wet towel. That twisting motion generates an incredible amount of pressure.
And the power potential here is just wow. Now, our own biological tissues can only handle about 5 megapascals of pressure, but Sato's model shows that if you were to build the same design with modern engineering materials, the theoretical limit is 55 megapascals. That's 10 times more powerful than our own bodies.
Okay, so that's the pressure part of the equation, but believe it or not, that's only half the story. The second big clue comes from looking at our skeleton, not just as a frame, but as a seriously clever piece of mechanical engineering.
Sato's other key insight comes from a totally different model, this one looking at pure mechanics. And what he found is that when your foot is planted firmly on the ground, that's what's called a closed chain condition. The geometry of your limbs, it changes everything. The specific angles of your hip and knee can redirect forces in ways that just seem to defy simple muscle logic.
And get this, the numbers are pretty staggering. In a pretty standard 45-degree leg press position, his model shows that the geometry alone, just the alignment of the bones, converts about 70% of that pulling tension from the hamstrings directly into a pushing force. This isn't biology, it's just pure physics.
So the key thing to really understand here is that this force redirection happens no matter what the muscle itself is doing. It's a property of the lever system of our skeleton. So now we have two powerful but totally separate clues, a pressure generator and a geometric lever.
Okay, we've got the pieces of the puzzle laid out. We've got pressure and we've got geometry. Now let's see how Sato puts them together into one single, elegant, unified theory. Now, this quote from Sato is the absolute core of the theory. I know, it looks a little complex, but the main idea is that our maximum pushing force is the sum of two very different things happening at once. Pressure stiffening coming from the calf and geometric transmission coming from the hamstring's pull.
So let's break that down. When you get ready to push, your calf muscle, the gastrocnemius, contracts. But because of that squeezing effect we talked about, it doesn't just get shorter, it gets incredibly stiff with all that internal pressure. It basically becomes a rigid pressure column. Now, when the hamstring pulls, it's not pulling on a floppy leg anymore. It's pulling across this rigid, pressurized structure. And that means the force shoots straight through the stiffened leg right to the ground, with almost no energy wasted.
And there you have it. That's the solution to the paradox. A pulling muscle can push because it's not working by itself. It's working through a system that has been temporarily turned into a super rigid, super efficient lever by hydraulic pressure from a totally different muscle. The two systems work together perfectly.
So, what does this all mean? What are the bigger implications?
Well, if this theory is right, it doesn't just solve one little paradox. It could fundamentally change how we think about movement itself.
We're moving away from that old muscle centrism idea to this new concept of structure-pressure centrism. And it suggests that peak performance isn't just about making one muscle stronger. It's about the perfect timing and coordination of pressure and tension across the entire structure of the body.
And this new perspective has some huge real-world applications. In sports, the focus could shift from just building raw strength to optimizing the timing of this whole body stiffening. In robotics, we could design powerful, soft robots that don't need any clumsy external pumps. And in physical therapy, we could use posture and pressure supports to help people tap into the power of their own geometry to make up for muscle weakness.
And hey, let's not forget that 55 megapascal number. Sato's research points to the idea that by really understanding and engineering these principles, we could create artificial muscles and superhumanoid actuators that are way more powerful than anything our own biology can produce.
Which kind of leaves us with one final big question to think about. This theory is really asking us to reconsider what our bodies fundamentally are. For more than 100 years, we've basically thought of ourselves as machines full of simple engines. But maybe a better way to think about it is that we're actually sophisticated self-pressurizing hydraulic systems, where geometry and pressure are the real secrets to our power.